Hi everyone, it's Math with AUB. Let's embark upon this one. Such type of questions present in analytical reasoning, number theory type questions, real analysis. Nowadays, discrete structure, discrete mathematics, such type of questions are present. We are asked to find, we are asked to prove that under root 2 is a rational number by the method of contradiction. We have two to three major types of proof. They are contradiction, second if then, in discrete mathematics it is known as implication, and double biconditional double implication, or it is known as if and only if, or one can say converses to, and the third one is final generalization, which is also known as mathematical induction. Without indulging into any controversy or lengthy introduction, let's do this one. Method of contradiction is that now we have to prove under root 2 is irrational. On the contrary, we suppose that 2 is a rational number and we arrive at a contradiction. So on this basis of contradiction, we say that under root 2 is a rational number. Like now I am making this video at night. At night, it is in the night time. If I got out and say that I have to prove that it is night, then I take the assumption on contrary it is day. If it is day and it is not so much cloudy, there must be a light visibility. I can see here and there without any trouble, and there were no stars visible in the daytime. I arrive at the contradiction because there was no light outside. I cannot see beyond some meter or so, owing to the presence of no light, owing to the darkness, and stars in the sky as well as in this day, and this night moon as well. So I arrived at the conclusion: stars are in the night, at the night, dark is outside, so it is not a day but night. It is the way of method of proving contradiction. We have to prove that under root 2 is irrational number by using contradiction. By using contradiction, whatever the rational numbers are, they are not like this 2 and 4. They must be like this, relatively prime. They must be relatively prime. If some table is applicable, then we cannot consider them rational number. It is the definition of rational number. They are relatively prime. They have no common factor except one. Or that is the case: 4 over 8, 3 over 6, 9 over 18. They are not rational numbers by definition. They must be relatively prime. They must be relatively prime. They must be relatively prime. No more table is applicable on them. They have common factor of numerator and denominator. Common factor is only one. Common factor is one. We can write m and n have GCD 1. M and n have GCD 1. M raised n is as rational number if and only if m n belongs to z and n does not equal to 0. Furthermore, they are relatively prime. They are relatively prime. We have to arrive at some contradiction in that case. Contradiction in that case. For rational number, they must be relatively prime. There must be no common factor except one. There must be no common factor except one. There must be no common factor except one in case of rational numbers. Now we are about to arrive at contradiction. Let's see how. Under root 2, we have to prove that it is irrational. On contrary, on contradiction, assume that under root 2 is a rational number. Under root 2 is a rational number. Under root 2 is a rational number. If under root 2 is a rational number, then we can write this in m over n form, where m and both belongs to z. Furthermore, n does not equal to 0, and m and n are relatively prime. They are GCD. Greatest common divisor must be 1, not more than 1. Okay. Squaring both sides. Squaring both sides. It is something like under root 2 square and m over n whole square. We have to is equal to m square and square. We can distribute this power to numerator as well as denominator. Okay, shift 2n square here. It will become 2n square is equal to m square. 2n square is equal to m square. Now our m square is multiple of 2, our m square is multiple of 2, our m square is multiple of 2, our m square is multiple of 2. So m square is even, so does m, so does m is also even. Here m square can be written as the product of 2 and n square. M square can be written as a product of 2 and n square. From this very line, we can conclude that m square is an even number because 2 divides m square. If I shift 2 here, it will become m square 2. M square is divisible by 2, or I can say m square is a multiple of 2. M square is a multiple of 2. So m square is even. M square is even. If m square is even, then it's square root. Then its square root must be even. Then its square root must be even. If m square is even, then m is also even. M is also even. If m is even, then I can write m as 2p. I have written m and another letter 2p. So instead of m, I can write 2p here. This is our 2n square. Instead of m, I can write 2p whole square. It will become something. 2n square is equal to 4p square. 4p square. Now pay attention here. Twist in the tail. 2 is the common factor. 2 is the common factor. 2 is the common factor. Here I can write as n square is equal to 2p square. For any rational number, they must be relatively prime. They must be relatively prime. It is a contradiction. It is a contradiction. 2 is a common factor here. 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 Look at this. 2 is a common factor, so we arrive at contradiction. For prime numbers, they must be relatively prime. For rational number, sorry, for rational number, for rational number, their GCD must be 1. Their GCD must be 1. But here, their GCD seems to be 2. Their GCD seems to be 2. They have 2 as a common factor. They have 2 as a common factor. So we arrive at a contradiction. It is contradiction by definition of rational number. They must be relatively prime. They must be relatively prime. Their GCD must be 1. Their GCD must be 1. Here it seems to be 1. Here it seems to be 1. It is a contradiction. So, by virtue of contradiction, under root 2 is not rational. Under root 2 is not rational. Means under root 2 is a rational number. Under root 2 is a rational number. We arrive at the proof by using contradiction. By using contradiction, under root 2 is a rational number by virtue of definition. If you factorize 1 times 2, 1 times 2, there are no more pairs available here. We can write our, as we are bound to prove this by contradiction. Suppose on contrary, under root 2 is a rational number. If rational number, it can be written as m over n. For these m and n, there must be a restriction. Their GCD must be 1. Their GCD must be 1. Their GCD must be 1. That is the key fact. That is the key fact. That is the key fact. Squaring both sides and manipulating. So from this line, from very this line, we have concluded that m square is a multiple of 2. M square is a multiple of 2 means it gives us, it implies that m square is an even number. M square is an even number. So does m, because square root of m square is m, which is also even by virtue of this definition. Here, if m is even, then I can write m is equal to 2p. If I plug in the value of m here, 2p, we have arrived here 2n square is equal to 4p square. 2 is a common factor. 2 is a common factor. 2 is a common factor. That is the violation of the definition of a rational number. That is the violation of the definition of a rational number, because they must be relatively prime. They must be relatively prime. They have no common factor except one. Except one. Here seems to be 2 is a common factor. We arrive at conclusion. We arrive at a contradiction. So under root 2 is a rational number. It's all by itself. Next.